Hello, everyone. Thanks for registering and participating in Networking at Scale 2022 Transport Edition event. My name is Bharat Parekh. I am an engineering manager supporting traffic protocols team at Meta. We are going to have a live Q&A with speakers of three talks we had earlier. The speakers are here with us. Welcome back, Jana, Joseph, Matt, and Yair. Thanks for the interesting talks on various aspects of Quick. It's exciting to see how Quick is shaping the transport space and enabling new use cases. My colleague, Luca Nicolini, is going to help us coordinate the questions from the audience during this. Let's get started with Q&A. Are you guys ready? All right.
Yep.
The first question I have is for Jana. Jana, you talked about the Quick enabling the agility and moving faster because it's in user space, one of the main advantage of the Quick. But it seems like there are some kernel implementation. There's already one kernel implementation, and as Quick get adopted more and more, there will be more Quick kernel implementation. How do you think the Quick would continue this impact Quick's agility and move fast and iterate fast?
Thank you for the question, and thank you for giving me time to change my clothes and grow my beard after the talk. I'll say that there are two things, right? Two ways to think about this. One is that there are Quick has versions, and that's an important thing. We can support, and we do in fact support right now, multiple versions on the internet. The internet has many versions of Quick right now. Meta has its version. Presumably there's some modifications that they've done, I'm assuming here, but I know that Google was running multiple versions at some point, and we have the IETF version 1. We have a version 2 that's coming out soon for IETF Quick. There will continue to be multiple versions of Quick. So even if some versions of Quick don't move as quickly because they are in kernel or various other reasons, we will have the ability to deploy other versions of Quick in parallel. And hopefully, if the benefits are there, they will get picked up wherever they do. So that's probably the biggest way I can think about the agility thing. The other thing I'll say is that for the network, our goal has always been to disallow the network from ossifying Quick. We'll see how things go. When I say the network, it's really a question of slow-moving parts of the end-to-end system, right? So it is possible, although hopefully when people are building in the future, they are trying to future-proof whatever they're building as well. So my hope remains that, even if built into various systems like firmware and other such things, upgrades will be possible that will allow people to actually deploy newer versions of Quick going forward.
Okay. Have you seen any sort of interoperability issues or with the kernel implementation of Quick so far?
I personally don't have any direct experience with these kernel implementations, but I would not expect there to be interop issues because they are basically, the protocol is still the protocol. Okay. And if there are interop issues with the protocol, then we need to go back to the spec and fix it.
Okay. All right. There is a little kind of related questions in the main aspect of the Quick design. And like, if you have to compare Quick protocol user space versus the user space DPDK and TCP user space TCP stack, do you think that achieves the same goal and performance benefits or other benefits?
That's an interesting point. So one of the important parts of how Quick was designed was one of the core things about Quick was for it to be agile, right? And performance is something that we can build by changing the protocol, by changing the congestion control, as we saw Joseph talk about, jumpstart and various other things. There are things that we can do to improve performance on the network, but on the agility in terms of being able to deploy things faster is what being in user space offers you. So sure, if you build things like a user space TCP stack, in general on systems, it is easier to deploy that newer modifications to that TCP stack. It still doesn't take away from one of the biggest benefits of Quick, which is that it right now will work on the internet, even if you modify it. That's a huge benefit. If you modify TCP right now, yes, you can deploy a modified TCP on top of your stack, but then try deploying it on the internet. And that's where you're going to have the most trouble. And so without encryption, without all the pieces that we put into Quick together to make it happen, it's kind of hard to recreate Quick. You can recreate various pieces of it independently, and some of the benefits you can pull by doing certain things, but the whole package is kind of hard to replicate in other ways.
I see. Okay, thank you. I'm going to ask the next question to Matt. This question is related to DSR, Matt. I know that I've been kind of the attempt to do the DSR for TCP as well in the past and to some level of success. What are the main building blocks in Quick that makes it more feasible doing DSR?
Yeah, so I think there's kind of two categories of things. So like John has been saying both in his talk and also in these questions, TCP is typically, when it's used, is implemented in the kernel, usually either Linux or Windows, something like that on the server side. And while it's possible to make modifications there, it's certainly not easy. And so when you're talking about having something like DSR, which is fundamentally a pretty basic distributed systems problem, achieving that in the kernel, while possible, is a lot more complex. And so Quick, when it's implemented in user space, already has that advantage to it. So now you could say, oh yeah, but you could just implement TCP in user space, and yeah, that's true. So the other category that makes it easier is the Quick protocol design. And there's a few things in there that make it relatively advantageous to do something like DSR with Quick versus TCP. So one thing that's pretty important is the protocol semantics, which in TCP you have a single byte stream, which you can multiplex on top of. But if you want a typical multiplex protocol like HTTP serving lots of content, you have to deal with basically this stream byte semantic for the entire connection and make sure that's consistent across all of your hosts. With Quick, you don't have to deal with this because the individual streams, which will each be written by an individual host in the DSR case, are completely independent of each other. So that makes reasoning about it, but also implementing it a lot simpler. And the other thing is that, like Jana mentioned, the way that we do TLS with Quick is fundamentally different from how it's done with TCP. So with TCP, you write relatively large TLS records into that byte stream, and doing that across multiple hosts, again, while possible, is more complicated than with Quick. Each packet is individually encrypted and individually considered. So that's a lot easier to basically offload because you can have this notion of the really simple packet writer that's just responsible for taking this, putting the data in, encrypting it, sending it off. And it's a lot easier to do with Quick without having crazy logic. So that's how I would say it's easier to do with Quick.
Okay, thanks, Matt. The next question, I think, is relevant to DSR, and in that probably, this is a question for you. It seems like mainly DSR introduced a lot of distributed complexity. Would you like provide a little more colors in terms of how the DSR design was approached to minimize the distributed complexity?
Sure. Yeah, so I think that at first glance, it might look like DSR adds a lot of complexity, but if you drill down a little bit more and understand how it's actually being implemented, then I think that the overall complexity is not that high. Basically, we have the solution is composed by two main entities, the backend and the front end. And the front end is responsible for making the decisions of when, what to send, and at what pace to send. And this basically the front end is in a sense the brain, and while the back end is just a dumb pipe. It is receiving packetization requests from the front end, and basically doesn't have to authority or responsibility to make any decision. It's just following the instructions that the front end made. So anyway, the front end is the logic without even DSR is the same at the front end, and the back end is just a dumb pipe following the instructions. So in a sense, there is not too much complexity added to the solution.
I see. Thanks, Yair. I have a relevant question here from the audience, and that's for DSR, any insight on how to debug errors, especially given that the streams are going to be from multiple cache backends? So when there is an error, how do you debug errors? This is probably Yair and Matt, both you can take. Yair, you want to start with this?
Yeah, so I think that there are like multiple layers, right, that we can look at. The transport layer, the application layer, and I think focusing at the application layer. So obviously at the beginning, like we had some stabilization or maturity issues that we ran into. And as time goes, we develop some techniques and some best practices to how to approach such problems. We introduced some instrumentations and debuggability capabilities as we went forward. I think that Matt can talk about the transport layer capabilities that we added.
Yeah, Matt?
Yeah, so thanks, Yair. The main one that's been useful is basically the same one that's been useful for us with Quick in general, which is QLogs. So Jana talked about this. They're incredibly powerful as a way to extract traces and pretty much arbitrary data from the transport. So what's nice about QLogs is they're super flexible, right? They're not just packets, right? They're not just like a log of packets, like a PCAP. You can add arbitrary information in there. And so what did we do? We added arbitrary information about DSR in there. So this lets you, when you find a problem, you can like turn up the QLog tracing, find the QLogs that are relevant to your problem, and look at them, see what happened. And then usually right away you're like, oh wow, this sequence of events doesn't make sense. And then you can figure out your problem. And so this can apply both to the front end, like you add QLog events to the front end, but you can also make it so that same QLog, depending on how your logging works, the back end, even though it's a different server, can add events to it, and they'll show up in that same timeline. And that's really useful because debugging is mostly about human readability, right? At the end of the day, in order to debug a problem, you want something that you can find patterns in and you can surmise issues from. And QLogs were the best way for us to do that and have exposed a lot of issues with DSR that we have subsequently fixed.
Okay. Thanks, Matt. Thanks, Yair. The next question we have is for Jumpstart, for Joseph. It's basic. It seems that the Jumpstart mainly is deployed right now in Meta's backbone and within the Meta's network. If you were to do this over for the internet, how would you do it differently? What will be the challenges, design challenges, and whether that would provide any benefits?
Yeah. So I think we make two big assumptions that are specific to the backbone network. The first is the paths don't change frequently, and that the capacity is almost static. Like the links don't change capacities as a connection is going or between connections. If we were to look at the internet, this is going to be different. The connection between a client and a server can change paths. Interfaces can go up and down. And the capacity can change for different reasons. So it wouldn't be exactly the same. For example, a client that is currently tracking its own congestion window across connections, the client can still do that but it will have to take into consideration how the links change if it's using a different connection. The other part is that congestion is now moved. Most of the congestion is going to be in the last mile, which the client can control. So on the client side, it's going to be pretty much the same, where the client can keep the state and reuse it based on the observations it makes. The big difference is going to be on the server side, because the client is probably talking to a VIP that's backed by a lot of servers. And not all of these servers can keep the state. And even if they do, there is very little chance that the client hits the same server over and over again. So it's not feasible for the servers to track, all of the servers to track the state for each of the clients. So one way to do it would be maybe to pass a cryptographic token from the servers that has the latest congestion control state to the client, and it's opaque to the client passes it back, and the next server can use it. Again, based on making observations on how the network conditions are. So it would take some changes. The big difference is, to summarize, currently both the client and server are doing pretty much the same thing in the backbone, and they rely on the link being relatively stable. It will change if we have to do that on the internet.
I see. Thanks, Joseph. There's another DSR related, not DSR, quick jumpstart related questions. How does this compare to TCP BBR? If you had a chance to compare the quick jumpstart and zero RTT with TCP BBR.
So I can take this question in two ways. BBR is a congestion controller. Jumpstart can work with BBR as well, and we've tested that. So the only difference is Jumpstart sets the initial conditions for the congestion controller, and then the congestion controller works as usual. So if I'm to compare Jumpstart on its own against BBR, BBR still has a startup phase. When it starts, it will take some time to probe the network. It is faster than Cubic, but it won't be able to use all the available bandwidth in the first flight. So in a sense, Jumpstart can work with BBR as well. We currently have not used that, because all the other TCP traffic in the backbone we have right now is Cubic. So we did not want to introduce another interaction between two different congestion controllers in the backbone. But yeah, I see these as two different things. It's not an apples to apples comparison.
Thank you, Joseph. Jana, I'm going to take another question. It's for you. It seems the Quick has integrated the crypto layer and transport layer both are integrated in one, right? They're not a separate layer per se in Quick. How does this create issues, especially when it comes to updating and rolling out security issues with TLS vulnerability or security fixes and such?
So I want to separate the protocol from the software, because this is really a software problem, right? So what we're talking about is how do you change your software? Just putting it in the transport doesn't make it fundamentally harder. However, putting it in firmware or hardware might make it harder. So it doesn't matter what you're updating. If it's running in a place which is easily updatable, then yeah, if there are vulnerabilities, then you can send patches out and you can update them. And that hygiene should be there wherever the TLS stack or wherever the security layer effectively or the security code lies.
See. Thanks, Jana. The next question is mainly for Jumpstart, for Joseph. For Jumpstart, have you guys compared the fairness of TCP, like quick Jumpstart flow, against any other quick flows that are non-Jumpstart? Do you see any issues? How does you deal with the fairness in there?
So to answer that, we are using Cubic as our congestion controller. So we are inheriting the fairness properties of Cubic. So for sufficiently long flows, a jumpstart and a non-jump-started connection will share the bandwidth fairly, just like any 2-qubit connections. For shorter connections, if I really want to compare this fairly, then I would compare jumpstart with a long-lived persistent connection that is between 2 proxies in the double proxy approach. And again, in this case, we maintain the fairness properties of QUBIC. All the jumpstart does is just it sets the initial congestion window and the minimum RTT value on the connection, and then it lets the congestion controller do its thing. So we're really not changing any of the fairness properties of the underlying congestion controller, which for now is QUBIC for the situations we've tested.
I see. Thanks, Joseph. The next question is related to DSR. As this is a question for you, Matt. Do you see any opportunities for quick cache DSR flows to be offloaded to smart NICs or data DPUs? And if so, how much of a performance gain can be achieved?
So I think this kind of gets at QUIC as an offload in general, offloading QUIC as a protocol. And I think this is an area where we're currently working on this. So the approach that we want to take when thinking about offloading QUIC is to constrain it in a way that hasn't historically been done for TCP. So like when people have talked about TCP offloads and TLS offloads, often what ends up happening is you'll have a NIC that is smart and will essentially run the protocol for you. And this, while the face of it seems like a good thing, it also kind of isn't really in the spirit of QUIC. You know, as we've heard time and time again here, like part of the core value proposition of QUIC is its agility and its malleability as a transport. And by putting that in NIC firmware and giving away that control, you're kind of you're not really retaining that anymore. So I think when thinking about offloads, you have to look at why are you offloading something, and the main reason you'd offload something with QUIC or with any transport is you're trying to reduce resource cost to the host. And the main places where QUIC incurs a resource cost is the same as TLS and TCP, which is copying the pages from the NIC from host memory to the NIC, so DMA, and crypto. And especially with QUIC, it's crypto because the way that QUIC encrypts packets individually is different and relatively more costly than TLS records because they span multiple packets. So the way we think about QUIC offload is that we want an ability for a NIC to get basically a sort of a plain text QUIC packet, unencrypted packets, and encrypt it inline for us. So, and then you can also, do the tricks where you have maybe shared memory. So you're also not incurring copies. You're just pinning pages and all of this. And then also the other part that would be very convenient for a NIC to do is to pace for us. So like we talked about pacing offload in DSR, which is where, offloading pacing to another host. Well, the same principle applies if you're offloading pacing to a NIC. So I think conceptually, they're actually pretty conveniently composable topics, which is to say that just like you can do DSR with another host, you can also offload packet writing itself to a NIC. So it's kind of just another layer of having another entity responsible for part of the process. So you can imagine a future where with DSR, we say, okay, this host is going to write these packets. And then that host then is responsible for constructing the packet, but actually it's not even responsible for all the pacing or the encryption. It then offloads that to the actual NIC, and that would further make it so that the relative CPU cost is even lower and would be at that point significantly lower than what you'd even do with just TCP and TLS offloads. So yeah, I think they're complementary topics, and it's something that quick offload is something that we're working on. But I want to be clear, it's something that we think should be constrained basically to encryption, so that we retain the core value proposition of QUIC as a changeable transport.
Thanks, Matt. It seems I think we are pretty much out of time. Thanks, Jana, Joseph, Matt, and Yair for having an interesting discussion and taking the questions. Thanks all the participants for asking the interesting questions. Please stay tuned as we have 2 more talks and another Q&A panel moderated by Luca later. Thanks everyone.